All right, let's look at this example. So we're investigating a contingency table. So the table relates the weights and heights of a group of individuals participating in an observational study. And so we're looking at two variables. One is sort of categories for weight, and the other is categories for height. So some of the numbers are filled in. So we want to kind of complete the table. And part A says find the total for each row in each column. So we add across. Calculator is useful. So 18 plus 28 plus 14. We get 60 for total of obese. 20 plus 51 plus 28. We get 99 for the total of normal weight. And 12 plus 25 plus 9. This is 46. Right. Now the totals for the columns, the talls, we get 50 in total. Mediums, we get 104. And the short, we get 51. Right? Now the big total, we can either add the rows and the columns of the total. It should give us the same number. And it's good to check both just to kind of make sure that we didn't add anything else incorrect. Yeah, 205 looks good. All right, so that was part A. All right, part B, find the probability that a random chosen individual from this group is tall. All right, so that means we're, for the whole group, out of the 205 people, you're counting how many tall ones there are. So there are 50 out of 205. So the probability of choosing a tall person at random would be 0.2439. Do that division. All right, part C. Find the probability that a random chosen individual from this group is obese and tall. So we're looking at how many obese and tall people there are. So there's 18 out of 205. So the probability of choosing one at random that falls in that category is going to be 0.0878. Find the probability that a random chosen individual from this group is tall given that the individual is obese. So when you see given, this is conditional probability. So we're trying to figure out probability a person is tall given that they're obese. So this condition reduces the sample space. So we're only looking at the obese category. There are 60 people in there. And you're seeing how many tall there are, 18. So the probability of, out of the obese group, of choosing somebody who's tall is going to be 0.3. All right, let's look at E. We need the probability that a randomly chosen individual from this group is obese, given that they're tall. So now we're finding this. P obese given then tall. So now we're looking at the group of tall people. So we're going to look at this column. There are 50 tall people in total, and 18 of them are obese. So if I just have the tall people in one row, the probability of choosing a person randomly that's obese would be 0.36. At F, find the probability that a random chosen individual from this group is tall and underweight. Right, with and, we are looking at the whole group again. So tall and underweight, there's 12 in the whole group, 12 out of the 205. So out of the whole group, if I'm picking a person at random, there is a 0.0585 probability that that person will be tall and underweight. All right, let's look at G. Are the events obese and tall independent? All right, so we need to check a formula. For example, if I have probability of tall is the same as the probability of tall given they're obese, then they're independent, okay? Or you could also check probability that a person who's obese is equal to probability of obese and tall. This will also show that they're independent. So there's like 3 different formulas you can use for independence. The third one is if a probability of tall and obese is the probability of being tall and the probability of obese. So it doesn't matter which one you pick, whichever is most convenient. Like we have numbers for some of them already, so we might as well. So from B, I have the probability that a person is tall. So this is 0.2439. From D, we have the probability of tall given obese, and this is 0.3. Alright, so we compare a number. They're not the same, but they are pretty close. So this is a hard one to say whether they're independent or not, because they are pretty close. So when we're going to investigate this kind of dependence later in chapter 11, okay, where we kind of do a more rigorous test of significance to see if things are independent or not. For now, we can say they're different because this is 0.24 and this is 0.3, and we can call them that they're not independent. But when they're kind of getting close, we need a better tool to figure out whether they're dependent or not. So I'm going to say they're different, which means that these are dependent. All right, so stick with it. If the numbers are different, say they're dependent. If they're like really close, like this is 0.2999 and this is 3, you go, it's like, yeah, they're not really different. They're rounding error. If you want sort of more of a guide on when and when not, say if this number here, if you round it to 2 decimal places and they're the same, then you can say they're independent. If you round it to 2 decimal places and they're different, say they are dependent. Okay, so that's my guide for you guys on how to answer those questions.